We next consider differentiation formulae that somehow include the chain rule in them, and for that let us again go back to the statement of the chain rule. Let f be a differentiable function of u and u be a differentiable function of x. Then you know what the chain rule states. It then states that f is also a differentiable function of x as a composite function, and its derivative with respect to x equals its derivative with respect to u times the derivative of u with respect to x. Now suppose that f is the power of some differentiable function u, where the exponent is some n. Well, you do not see f here, but we are considering the dependent variable name here and not the function itself. If you want, you can write f here. So f is u to the power n. In this situation, if we apply the chain rule, what shall we get? But you have to be careful. You have to go carefully, taking into account everything. Okay. We know that u is a differentiable function of some variable x, and f is this particular function of u to the power n. How do we know that f is also differentiable? Well, that comes from your product rule for differentiation. You recall the product rule. If you take two differentiable functions, then their product is also differentiable. You can extend that rule to the product of any finite number of differentiable functions, n functions say. That will also be differentiable. So that way, in particular, u to the power n is also differentiable because u is differentiable. So we can apply the chain rule here. What shall we get? Obviously, we are again going to get this, but now we know exactly what this dy du is. From our usual power rule for differentiation, this equals n times u to the power n minus 1. And along with that, of course, you also have du dx. Now, it looks like a simple observation, a special case of the chain rule, but you will be surprised to see how drastically this can reduce our differentiation effort and time. And let us illustrate that with an example. This example has 4 parts, and this is the first part, where we are trying to differentiate the 5th power of sin x. It is of this form, u to the power n, where u is sin x. Sin x is differentiable, you already know, at every real number x. So its 5th power will also be differentiable, and by this rule, that is equal to 5 times sin to the power 4x times the derivative of sin x with respect to x, which is cos x. So do you realize how easily we have got this in just 2 steps? As opposed to this, if you think of applying the product rule here, which you can do, how many times do you have to apply the product rule? Say you can treat this 5th power of sin as sin x times sin to the power 4x. So then you apply the product rule once, and then you have to differentiate sin to the power 4x by again applying the product rule. It will be very long. You can understand that. So already you can see how powerful this thing is, and this is what we use all the time when differentiating powers of differentiable functions. Let's see the next one. So the next one is this function, 2x plus 1 to the power minus 3. So here the exponent is negative, but after all it's the power again. So by our rule, minus 3 times 2x plus 1 to the power minus 3 minus 1, that means minus 4, times the derivative of the thing whose power you are considering, that is 2x plus 1. Now this differentiation gives you just 2, of course, because differentiating 1 you are going to get 0, and differentiating 2x you get 2. So that way this is your derivative. Now you think of how you would normally differentiate without using this rule. you would have to write this power as 1 divided by the cube of 2x plus 1, and then you will have to use the quotient rule, and then you have to deal with the cube, because you see, in the numerator somewhere you have to differentiate the cube of 2x plus 1, which however you cannot do without expanding the cube. So how long the calculation would be, you just think of it without this. Here however, you just in 3 steps you have got the answer. Next we have this one, the derivative of the 7th power of 5x cube minus x to the power 4. Just imagine how daunting the task would be without this rule. If you want to differentiate this, how many times can you afford to apply the product rule for differentiation? If you break this power down as a product of 2 things. So instead, you may think of expanding this. So you may use the binomial theorem, or you can just try to do the multiplication. It becomes very messy. So instead, we have this neat rule. So 7 comes down, and then you subtract 1 from the exponent. So you have 6 here, and then you differentiate this inside. So that gets you what? 3 comes down. Again we are using the ordinary power rule in differentiating this part. Gets multiplied with 5 gives you 15, and then it gets reduced by 1 there in the exponent. So it's x square. And again similarly this one becomes 4x cube. And that's it. And there is one more. And finally in part D, we have the derivative of 1 divided by 3x minus 2. You can immediately see that it's not really that hard in this case. You can apply your usual quotient rule. But still, let's see what we get if we apply our new rule. This reciprocal, of course, is this power where the exponent is minus 1. So minus 1 times 3x minus 2 to the power minus 1 minus 1, that means minus 2, times the derivative of 3x minus 2, which is 3. So that way we get minus of 3 divided by 3x minus 2 whole square. So you can see that even if you apply the quotient rule instead, you are in fact getting a square, the square of 3x minus 2 in the denominator. So there at least these things are matching. Matching means of course they will be the same, but we can immediately see that yes, we are going to get the same answer. So with this, let me just end this video. Now in this section, what else do we have? Oh, we have that ice melting application that we will see next week. So see you next week with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.